Okay, so last video we had a bit of background about where the process comes from, and now we're going to dive a bit deeper into how you would approach these questions on an exam. So for instance, if you're coming across the exam, which is shockingly in 2 weeks, and it says solve the system of differential equation that looks like this, what you would do is you would need to find the eigenvalues and the eigenvectors of this matrix. So we'll break it up into 2 steps. Why not? We'll do find the eigenvalues first, find the eigenvectors, and in doing so, make sure it's defective or non-defective for the purposes of this video. So what we'll do in the next video is figure out when it's not, or when it is defective, I should say. But for now, we're going to focus on just the non-defective case. Okay, and then after that, you say x is equal to c1 e to the lambda 1t times v1 plus c2 e to the lambda 2t v2 and so forth for as many dimensions as you need. All right, so we have our matrix A. So for step 1, finding the eigenvalues, we take the determinant of A minus lambda I, which is this here, 0 minus lambda. I'm just going to call it minus lambda. Minus 3, 1, negative 2, minus 1, minus lambda, 1, 0, 0, 2, minus lambda. And I need to set that equal to 0. So to save some time, again, we know how to take determinants. What we get is we have lambda plus 3, and then lambda minus 2 squared is equal to 0. So my first eigenvalue is negative 3 with multiplicity 1, so that's fine. Lambda 2 is going to be 2, and it is multiplicity 2. So this here raises a flag. I'll draw a little flag here. Why not? But, we can lower that flag if we're able to find 2 linearly independent eigenvectors. So this one's fine, but I need my geometric multiplicity to equal 2. So what we can do, and you'll guess because we're in the non-defective part, we will find them. But we'll start with lambda 1 is equal to negative 3. So I find the eigenvectors in the same way I always have done. Is A plus 3 times the identity, which is, let me pull it up here actually, 3, negative 3, 1, negative 2, 2, 1, 0, 0, 5. So I'm going to call my eigenvector v1, I'll do 1, 1, 0. Makes the most sense based off this choice. And lambda 2 is equal to 2. So I have A minus lambda 2i, which is A minus 2 times the identity, which gives me negative 2, negative 3, 1, negative 2, negative 3, 1, and then a row of zeros at the bottom. Okay, so remember, we need to be able to find 2 eigenvectors here, and they need to be linearly independent. So what I'm going to do, and what I'm going to get in the habit of doing, in fact, is checking the rank and nullity of this matrix here. So I don't even have to really row reduce, right? Because I know I have a row of zeros. So I know my nullity has to be at least 1. My n is going to be equal to 3 because I have 3 columns and 3 rows. But I have 2 rows that are scalar multiples, right? So that adds an additional thing to nullity. So my rank will be 1, my nullity will be 2, and n is equal to 3. So everything works out well there. What I care about is this nullity being equal to 2. That confirms that I should be able to find 2 linearly independent eigenvectors for this. Because remember what we're doing, and I'll do a quick recap. A minus 2i times some vector v has to give me 0. So my eigenvectors are living in my null space. So if I have nullity of 2, then I should have 2 vectors living in my null space. So I can go ahead and pick those vectors from this matrix here. So I'm going to pick one to be 1, 0, 2, and I'm going to pick the other one to be 0, 1, and 3. So all I'm doing to make sure they're linearly independent is I'm putting a 1 in the first column here. And then the easiest way for me to get rid of the rest of it is to put a 2 here for this one. And then the same process works for V2 as well. So if you haven't already gotten really good at doing this, you will in this chapter. Like really, really good. So there's a bonus, I guess. All right, so we have our eigenvalues and we have our eigenvectors, so we can construct our solution already. So we have, let's go ahead and just recap our pairs. We have lambda is equal to -3, and V1 was equal to 1, 1, 0. I misnamed these, sorry, these should be V2 and V3. I have lambda 2 is equal to +2, and I have one eigenvector, whoops, again, V2 is 1, 0, 2, and V3 is 0, 1, 3. So my solution then will look like x is equal to C1 e to the -3t times 1, 1, 0 plus C2 e to the 2t times 1, 0, 2 plus C3 e to the 2t 0, 1, 3. Okay, and then we can put these all together into one big matrix here, or vector here. C1 e to the -3t plus C2 e to the 2t, C1 e to the -3t plus C3 e to the 2t. So now it comes from this term. And then I have, I have 2C2 plus 3C3 e to the 2t. So just combining this part and this part here in my last term. So I have what size vector here? I have 3 rows, and all of these actually add, and this is just one column, no matter how wide it is. That's correct, right? Because I should be having 3 solutions, x1, x2, and x3, all as functions of t, because if you remember, we go back up and we had a 3 by 3 case here. So that was the whole process right here. Notice that we had repeated roots. Okay, so flashback to chapter 8. We came up with this determinant here. And if we compare that to the auxiliary polynomial, we would have 2 different roots here. So you would expect I would have a t somewhere in my solution, right? I would have C1e to the 2t plus C2t times e to the 2t, right? Because I have repeated roots. We'll see that is the case when we're working with defective matrices, but we're saved from doing this and making our solution more complicated. We're saved from this because we have a non-defective matrix, namely this V3 right here is linearly independent from this V2. So that's how we're able to cover our solution space, because we have everything linearly independent, all right? So next video, we'll talk about non-defective matrices, which make your life a whole lot harder, but we'll still solve them in a similar manner here.